Okay, last set of questions. Better show some work on this one. We have a 0.15 kilogram mousetrap car. It's wound up and held motionless at a starting line. When it's released, its mousetrap motor pushes it for the first 3 seconds. During that time, the car goes 12 meters. After the motor stops pushing, the car continues to coast for another 8 seconds. What's the average velocity of the car while the motor is pushing? So, average velocity equals distance over time. So we want to know the distance over which the motor is pushing and the time over which the motor is pushing. And the mousetrap pushes it for 3 seconds and it goes 12 meters. Distance is 12. The time, distance. And I'm going to put T1 there. You'll see why in a little while. 12 over 3. 4 meters per second. That's the average velocity. Now, 46 asks, what is the change in velocity during the car's acceleration period? If the car starts out at, here's the car, sitting still. It's going 0 meters per second. And then it accelerates to some maximum speed at the end. It's going really fast then. Its average velocity is 4 meters per second. It's going to reach that about halfway through. Half the time it's going to be going less than the average velocity, half the time more. So it's going 0 in the beginning, 4 in the middle. By the time it gets to the end, it's going to be going 8 meters per second. Just double this average velocity and you get the final velocity. So the change in velocity, final velocity is 4 meters per second times 2, which is 8 meters per second. Now this is also the maximum velocity, and that's also the change in velocity. It's going from 0 to 8, so it's adding on 8. So this is also the change in velocity. Now I'm jumping ahead here, but as the car starts to slow down at this point, it's moving pretty fast here. It's going to go from going really fast down to the end point where it's going to stop. So it's going to have a velocity of 8 meters per second, and then at the end it's going to go back to 0 again. And the change in velocity at the end is going to be 8 meters per second again, except it's going to be negative. Here, change in velocity is 8 meters per second, because 8 meters per second gets added on. In the end, during the deceleration period, change in velocity is negative 8 meters per second, because 8 meters per second is going away. We don't really need that information yet. But I was just getting number 46. So the way you get the change in velocity is to do the average velocity times 2. 47. What's the car's acceleration while the motor is pushing? Acceleration is meters, those are the units. Change in velocity divided by change in time. So the change in velocity while the motor is pushing is 8 meters per second. Change in time, motor pushes it for the first 3 seconds. That's the time we want for the acceleration period when the motor is pushing. 8 over 3, that's a little bit of a weird number. So 8 divided by 3 equals 2.6666, repeating, so I'm going to call it 2.67 meters per second squared. That's the right unit for acceleration. Ooh, I should be putting my answers here, right? 4 meters per second, 8 meters per second, 2.67 meters per second. What's the net force acting on the car? Number 48. Only got one formula for force, so that's the one we have to use. Force equals mass times acceleration. We just figured out the acceleration of the car, and you're given the mass. Here's the mass. It's 0.15 kilograms. Multiply that by my acceleration. Still have that on my calculator, so I'll just multiply it by 0.15. 0.4. And the units of force that we always use, assuming we used kilograms and meters per second squared, are going to be newtons. Let me check that. That just seems too good to be true. Nope, not too good to be true. 0.4 newtons. If you get a point, put the 0 and then the decimal point and then a 4. If you just do the decimal point, somebody might not notice that it's there. 49 is asking us the change in velocity during the deceleration period. Well, that's easy. If all this car is doing is speeding up and then slowing down, if it's still in the beginning, it speeds up and then it slows down and stops again, whatever the change in velocity was in the beginning, 8 meters per second, we're going to have the same thing at the end, except it's going to be negative, just as I was describing earlier. So this is going to be negative 8 meters per second. It adds its speed and then it subtracts its speed. I'm not going to show anything there. What will I do? Maybe I'll just say negative, make this, make, 50. What's the car's acceleration during the deceleration period? Well, that's easy too. Acceleration, same formula as before, always. Change in velocity over change in time. We've got the change in velocity. It's negative 8 meters per second squared. This is the little bit tricky part. Remember when I said I'm going to call this T1? That's because this other time, we've got another time in the problem here. I'm going to call that T2. So T1, 3 seconds, that was how long it took the car to get to its top speed. Here it says after the motor stops pushing, the car continues to coast for 8 seconds. 8 seconds is the amount of time it takes to slow down at the end. That's what we want to use. That's the number. So this is the change in velocity during the deceleration period. And 8 seconds is the amount of time it takes it to slow down. That's easy. Negative 8 divided by 8 is negative 1. Whoops, I messed up. Shouldn't be that. Change in velocity as meters per second. And when we get this acceleration, it's meters per second squared. That makes things easy. Negative 1 meter per second squared. What's the net force acting on the car during the deceleration period? You just take force equals mass times acceleration. I'm not going to write it again. The mass of the car, still the same mass. Multiply that by the acceleration we just got, negative 1 meter per second squared. And that's going to give us negative 0.15 newtons. So the force of friction is pushing the car backward with a force of 0.15 newtons. Haven't shown this, so maybe I'll draw a little picture here. This is the car at the end, or during its deceleration. It's slowing down, it's moving to the right, but the force of friction is pushing it back that way. That's the net force at the end. And it's also the force of friction. It's the net force and the force of friction because there's only one force acting on this car, and that's friction. If there were two forces, something pushing it forward and something pushing it back, then it'd be a different story. 52, going to be the same as 51. What force is provided by the car's motor? And now I need to do a more 52. 53. So I'm going to draw a picture of the car when it was accelerating. Back when it was accelerating, we calculated what the net force on the car was. It was 0.4 newtons. So I'm going to draw that. That's the net force. At that time, we had the motor pushing it forward, and we had friction pushing it backward. Now we've just calculated that this car has a force of friction of 0.15 newtons backward, or negative 0.15 newtons. So in the beginning, the motor was stronger than that friction. We know that because there was a net force forward. This net force forward of 0.4 newtons tells us the motor was stronger, and it tells us by how much. 0.4 is the difference between these. So this was 0.4 more than that. To get this, all we have to do is add 0.4 to this, and that'll tell us the motor's force. 0.4 plus 0.15 is 0.55 newtons. So 0.55 newtons is this many newtons stronger than that. That's the answer to 53. All right. Now we have a tricky but simple one, I think. Car's engine is pushing it forward with a force of 400 newtons. The car has a mass of 500 kilograms. It's moving at a constant velocity. What total force of friction is acting against the car? So that's actually an easy question. You don't need to know this at all. It says it's moving at a constant velocity. That means it's going, velocity is speed and direction, so it's going the same direction at the same speed, so the forces are balanced. So if the engine is pushing it forward with 400 newtons, to balance that, the force of friction must be 400 newtons backward. I don't need to draw a picture for this. Now if the same car had an acceleration of 0.1 meters per second squared, what would the force of friction have to be? That one is a little bit trickier. So if the car had an acceleration of 0.1 meters per second squared, then the net force we can calculate with this, and we'll go from there. So the net force is equal to the car's mass, 500 kilograms, times 0.1 meters per second squared, which would give us 50 newtons. That's the net force. And the car's engine is 400 newtons. So this will be the car. I'll make it look more like a real car, except weird. Alright, good enough. So the engine's moving it this way, 400 newtons. I've taken up too much room up there, so I'll put the net force down here. Net force is 50 newtons forward. So that tells me that the engine is the stronger force, stronger than friction. And it's stronger by 50 newtons. So the force of friction has to be 350 newtons. That's not a really hard bonus question. All right, that's it.